Today on Steve Robb Reviews, we're going to have some fun with some math. We're going to have some fun with solar panel. I've got a 7-watt solar panel here that I used on a project. I believe it was early in the year. I built this trail cam solar powered or solar charged battery that provides all the power to the trail cam, and there's no use for having any more batteries inside your trail cam. You can run it strictly off your solar panel with a 12-volt battery. And what I did was I got a drop-down converter from 12 volts to 6 volts, and I got a plug that goes in. If you want, I'll put a link down below and show how I built that. And it worked terrific up until it started to get cold. As you know, batteries have less capacity as it gets colder. And as the sunlight actually is reduced from the summer to coming on to the fall, well, you have less sunlight hours. If you want, I'll put a picture in here and I'll show you the setup I have. Let's take a look. Okay, so that's the picture of the setup I have, and it's just a 7-watt panel sitting there, and it worked fine during the summer. But I monitored it during the fall, and it started to drop and drop and drop because of the sunlight hours. So we're going to investigate what happened there and what you actually need. So let's get over to the bench here. I got everything all set up. I'll explain it. And you know, this would be pretty interesting for a lot of people who want to get into solar systems and solar power and just get a little bit of an idea of the variables that you have to consider when you're going to use solar panels and the capacity that you actually need. So let's get to it right now. Well, let's get started right here. Instead of using a battery, I'm just using my power supply. I've got my meter hooked up and I've got it on amperage, which is milliamps DC. And this is the solar panel that I used, a 7-watt panel. And here is my trail cam, and this is the little bit of converter. I showed this on my my video on how I built this, but this is the drop-down voltage supply that takes it from 12 volt down to 6, because you need 6 for a trail cam. So as you can see, as it's just sitting right there, 23.37, and it will show you exactly what the milliamp draw is. Now that is without the trail camera actually being on. It is off right now. The only thing that's drawing power is this right here. So that you might find interesting just to start. And so we'll turn the trail cam on as if you were just going to set up the menu for it. And you can see it spikes up to 171 milliamps, and it's going to be around 92 milliamps. So now we'll turn the camera actually on, and it's taking a picture right now, which lasts roughly about 6 seconds, 5 seconds, and then you're back down. Now I have done this a couple of times already, and if you wait over time, you'll get a proper average, and that's what I'm using, and this is using the averages. So as you can see, this is the particular setup, and these are the numbers, and this is what you have to know. So let's get down to the paper and pencil here, and let's figure out exactly what just happened. Well, let's take a look at the numbers, and let's start right off at the battery. A 12-volt battery, 5 amp hour. So we got the camera off. So the camera is off, and the only thing that's drawing power is the drop-down converter from 12 volt to 6 volt. And this is how much it's drawing here, 23.715 milliamps. So now we turn the camera on, and you can see it's gone up. So just say roughly 100 milliamps when the camera is powered on. Now a camera takes a picture, and this is what it spikes up to on average, which is 84.38 milliamps, but that's only for 5 seconds. So let's go to the next page and let's see what that looks like. Well, the first thing we've got to do is we've got the 7-watt solar panel. So you take 7 watts, you divide it by your voltage, which is 12.6 for a fully charged battery, and you're going to have 0.555 amps or 550 milliamps, or roughly a half an amp. So now, if you have 8 hours sunlight during the day, full sun, 550 milliamps per hour will be charged to your battery. And if it's shade, what I've noticed over time is on all my solar panels that I've looked at, is in shade you get roughly 8%. So it'd be about 44 milliamps charge going into your battery. So what kind of sunlight do you expect to get? Well, in the summer months you can expect an average of 5 hours of sunlight, and in winter 1 hour of sunlight. So we really have to use the lowest sunlight charge time, which is 1 hour, and that's in full sun. And this is what we're going to use for our testing. Okay, so right here we've got the camera on 23 milliamps. You take your 23 milliamps, you multiply it by 24 hours in a day, and you need 571.68 milliamps, or just over a half an amp, to run this camera for 24 hours. So if we take a look at 8 hours sunlight, we're just using that for an example, you got 44 milliamps times 8 hours, 352 milliamps. Now you could see you're running short right here because you need this much, and what do we got? 352. So if you take 12 pictures with the camera at 84 milliamps, well, you're 1012.56 milliamps, or about an amp every time you take 12 pictures. And of course 5 seconds a picture equals 60 seconds or 1 hour, and that's reasonable, 12 pictures a day. So let's go on to the next one. Well, here we go with the total amperage needed per day. So just for the camera itself, just being on, is little more than a half an amp, which is 571.68 milliamps. And so you take 12 pictures. So you know what? You pretty well need about 2 amps per day, and you need about a 30 to 40 watt solar panel, not a 7-watt solar panel. And why is that? Well, when you're working with solar panels, there's so many variables that go into the amount of capacity of your battery, the amount of wattage of your solar panel, and your load. And this is a very difficult one to actually narrow down, is because your load's not really fixed. It depends on how many pictures the camera is taking, and of course the amount of sunlight hours. And then you have the direction of your solar panel. Mine is fixed. If you notice in the picture there, mine is fixed at one location. And the best sunlight is actually having a variable one that can follow and track the sun. But that's a whole different ball game, and it's a lot more expensive to do. The cheapest way to do it is like what I did on my cabin, is I got it fixed, but I have an overcapacity. On my cabin I can produce, like I say, on a good sunny day, 25 amps, but it gets cloudy out, and of course there's different variables of cloudiness that I found. It can still be cloudy out, but there's, if you take a look at your amperage reading, like when it's cloudy, sometimes my panels will only charge, say, and I've got a 400 watt capacity, maybe 1.2 amps, and other days when it's cloudy, maybe 2.2, 2.3 amps. So yeah, I figure around 8% on a cloudy day. So you have to actually build in extra capacity. So during the summertime, this worked fine at 7. But as it got colder and as the daylight got shorter, the arc of the sun light moving over the fixed panel changes over time, and that played a big role in the amount of recharge that I was getting from the solar panel to the battery. So it was a great experiment to show there's so many variables involved, and you have to do a lot of testing yourself, and it all comes down to a lot of math and theoretical design, because you can't depend on a fixed amount of sunlight. You can't depend on a fixed amount of shade either, can you? And also you have to include temperature, direction of sun. So it is not so easy, but it's so much easier if you build it if you build it a higher capacity. So I'm confident that if I were to make this a 30 watt or 40 watt system, I'd have no problem at all. I'd have excess capacity. And that's really what you need, because once you start to reduce your capacity to the point where the battery's being discharged and it can't recover the next day because you don't have the proper sunlight, for instance. So your battery will slowly discharge over time and then the unit will just stop. And it's no good for the battery. And you know what? You live and learn, right? And you have to experiment with math and experiment with what you have. So if you'd like to take a look at the different experiments I've done on solar systems, I got a playlist down below. I'll put that down below with the video of me building this Trailcam battery solar panel charger. And I like doing this kind of stuff because you learn as well as you go along. And I kind of thought 7 watt in the beginning might be a little bit on the low side. It worked fine during the sunlight hours of the summer. And then as the fall creeped up, no. I went out there temporarily every once in a while and just checked the voltage of the battery. Yeah, it was going down. I knew I was in trouble. So thanks for joining me here today. I hope you enjoyed this little bit of an experiment. If you haven't seen this channel before, well, you're welcome to subscribe. Come back again and let's have some more fun. Cheers.